Okay, so now that we're familiar with how SAGE works in terms of defining mathematical functions, let's apply this to a problem that we could do by hand, but it's maybe easier to have the computer do. And that is, what we're going to do is take the standard basis for P4, and we're going to apply the Gram-Schmidt algorithm to it. I like to use the variable t. I'm not a big fan of the variable x, so remember, we have to tell SAGE what our variables are. Now let's go ahead and define the standard basis. All right, there's going to be, it's P4, there could be 5 elements of a standard basis. So I can make multiple definitions at once just by using the ordinary enter, and then I evaluate with a shift enter. So those are the standard basis elements. Now let's go ahead and throw them all together. So these square brackets, that's how we make a list. So let's see, what is standard basis? What does SAGE think that is? Notice it's a list of 5 functions. Each one of them is a function. You can tell because it's this notation with the arrow. Now, how do you do Gram-Schmidt? Well, you need to be able to take inner product. So we better tell SAGE what our inner product is. And here's where we have the second kind of function. The functions like x1, x2, etc., those are symbolic functions or mathematical functions. We also need to give SAGE functions in the sense of computer programming. So you do that with the keyword def. So I'm going to define what it means to take the inner product of 2 functions. And the way you make a definition is you use the keyword def. You tell me what the name of the function is, in this case IP for inner product, and you tell me how many inputs it has. So in this case, 2, F and G. So what am I going to want to do? Well, I'm going to do some computation, and then I'm going to return a value. So the very last line of any definition has to be return. What am I going to return? Well, what do? We want to integrate f of t times g of t. That's standard inner product. And we're doing this on the interval from 0 to 2 pi, so that's how we have to integrate. There we go. Okay, so it knows the definition. Now let's go ahead and apply that definition to a couple of examples. So let's do x1, x2, see what we get here. 2 pi squared is the inner product of x1 with x2. We also need to know norm squared. Well, that's pretty easy. So what's the norm squared of a function? Nothing more than the inner product of that function with itself. And we'll go ahead and compute norm, which is just the square root of the norm squared. So for example, we can ask, what is the norm of x5? We get an answer. It's got a lot of pi's in it, as you would expect. All right, now we're ready for Gram-Schmidt. So what is Gram-Schmidt? Well, Gram-Schmidt takes in a basis. You start with a basis, right? So we'll call that basis B. The first element of the Gram-Schmidt basis is just the first element of whatever your original basis was. We're just going to say we start with that first one. Now, what is the Gram-Schmidt basis going to be? It'll be a list. So I've used these square brackets here. And we're going to start off with just one element in that list, namely B0. Now, things are indexed in SAGE starting at index 0. So B brackets 0 means the first thing in B. And then what are we going to do? Well, let's figure out, we need to know how long B is, right? How many elements are in this basis B. So we use that with the command len for length. We'll call that K. Now, once we have the length of B, that's going to tell us when to stop, when we have enough elements, right? So how does Gram-Schmidt work? Well, until we get there, right? So we're going to start with the number 1, and we're going to end when we get up to the length of B. We have to do something. What we're going to do is we're going to take the jth entry of B, and we're going to subtract off the projection of Bj onto the span of the partial basis that we've built so far. How do we compute that projection of Bj onto the part of the basis we've built so far? Well, it's a sum. And the way you build a sum in SAGE is you need to feed it a list of things to add together. So if you write sum of a list, then SAGE will spit out, it goes down the list, adds everything up, and spits it out. So what are the terms that we're adding up? They're going to look like you take the inner product of Bj, that's the thing we're projecting, onto whatever the basis so far element is. You divide that by the norm squared of that basis element and multiply it by that basis element, and you're going to do that for all of the current basis so far. And by so far, I mean this index I only goes up to j minus 1. So that's how you get the projection of Bj onto the span of the part of the basis we built so far. And what do we want to do then? We want to add that to the current basis so far, which we use using the word append. So append means to take an element and stick it onto the end of a list. Okay, now we're done. So we want to return whatever we have. And I want to point out something here. I've tabbed back. SAGE cares about tabbing. Let's check it out. What is the Gram-Schmidt applied to the standard basis? There we go. You see we have how many functions? 1, 2, 3, 4, 5. 5 functions. We needed 5 functions. Voila. There's also a normalized Gram-Schmidt basis where you make everybody length 1. So let's do that simply by defining for SAGE what it means to normalize a vector. Simply to divide it by its norm. And how do we make the normalized Gram-Schmidt? Well, what you're going to do is you're going to normalize each vector v for each v in the Gram-Schmidt basis. Let's see what happens there. There we go. You see we have, they're similar, right? Of course, this is 1, and this one is normalized, so it's just a multiple of 1. This is a multiple of minus pi plus t, etc. So there we go. We've produced the Gram-Schmidtified basis, either the normalized one or the unnormalized one, which started off from the standard basis for the polynomial space P4.